Good evening, and welcome to Drift into Science. I'm glad you're here. Before we leave the ordinary day behind and drift toward the stars, you might notice where you are right now, perhaps already beneath the covers, resting on a sofa, or listening quietly through headphones as the room grows still. Wherever tonight has found you, I hope the busiest part of the day is over. There is nothing you need to solve or remember here. You can simply listen, let the ideas pass slowly by, and allow science to become part of the background as you settle in. Tonight we are going to move outward in scale, not toward one planet, one star, or even one black hole, but toward structures so large that each can hold billions of hundreds of billions of suns. We are going to follow the long life of a galaxy, and the story begins before any galaxy existed at all. We will move from an almost featureless young universe into a cosmos filled with dark matter. The first stars, growing disks, collisions, quiet aging, and eventually the slow fading of star formation. Along the way, we will watch tiny differences in the early universe become enormous structures. We will see invisible matter gather first, gas fall inward, stars appear, and young galaxies slowly organize themselves from something chaotic into something recognizable. Some galaxies will grow by drawing in fresh gas. Others will swallow smaller neighbors. Some will become graceful spirals, while others will lose that order entirely. And much later, we will return close to home, to the Milky Way and Andromeda, and the future still waiting for both. So let yourself get comfortable. Here is the question we will carry with us. How can a galaxy be born when there is no single instant when it suddenly appears? How can it grow into a city of stars? And when astronomers say that a galaxy has died, what has actually ended? Seen from far away, a galaxy can look almost timeless, a bright shape suspended against a dark background. But that still image is misleading. Our galaxy is a moving, evolving system, continually reshaped by gravity, gas, star birth, stellar death, encounters, and enormous stretches of time. It is useful, then, to imagine a galaxy as having something like a biography. It assembles slowly, grows unevenly, changes appearance, takes in smaller companions, passes through active periods, and may eventually enter a far quieter phase in which very few new stars are being made. Even the word galaxy can make us think only of stars, because stars are what we see. Yet the luminous points are just one layer of a much larger system. Between them lies gas in many conditions, some chilled into dense clouds, some so hot that its temperature reaches millions of degrees. Mixed through that gas is dust, made from microscopic grains carrying elements produced inside earlier stars. There are white dwarfs, neutron stars, and black holes, the remains of stellar lives that have already ended. Magnetic fields cross vast regions, and energetic particles stream through them. In the centers of many large galaxies sits a supermassive black hole. But even if we could map every star, cloud, remnant, and particle, we would still be missing most of the gravitational framework. Far beyond the visible galaxy extends a much larger envelope of dark matter. Dark matter gives off no ordinary light that telescopes can simply photograph. We do not see it glowing, blocking starlight, or reflecting radiation in the familiar way. Instead, we infer that it is there because of what its gravity makes other things do. Stars, for example, orbit too rapidly for visible matter alone to explain. The motions of galaxies inside clusters tell a similar story. So does the bending of background light around massive objects, and so does the way cosmic structure grew over time. A bright spiral image, beautiful as it is, shows only the luminous center of a much larger gravitational arrangement. Galaxies also occupy an astonishing range of scales. Some dwarfs contain only a few million stars, with the faintest systems holding even fewer. At the other end are giant galaxies containing hundreds of billions of stars, and in extreme cases the count may reach well into the trillions. But size is not the same thing as age. A small galaxy is not automatically young, and an enormous one is not automatically ancient. Two galaxies with similar masses can look completely different, one blue and active, another red and quiet, one rich in cold gas, another nearly depleted. Our histories can differ just as much. One may still be forming stars at a steady rate. Another may have spent billions of years dominated by older populations. So the life of a galaxy is not a neat ladder in which every system follows the same sequence from small to large and then simply stopped. A star has a comparatively clear beginning. A cloud contracts or protons or forms, and eventually fusion becomes sustained in its core. Galaxies are less tidy. There is rarely a single moment that deserves to be called the instant of birth. Instead, a galaxy comes together piece by piece. Gas settles into growing gravitational wells. Stars emerge inside that gas. Smaller structures merge, while fresh material continues arriving from beyond. Satellite galaxies can be captured, stretched, and stripped apart. Some encounters merely add new stars, others rearrange the entire system. And all of this may continue for billions of years. Galactic death is equally gradual. When astronomers describe a galaxy as dead, they do not mean that it vanishes or that every star suddenly goes dark. The change is quieter than that, and in many ways more interesting. Usually the word refers to a galaxy that has become passive or quenched. New stars require reservoirs of cold, dense gas. If that gas is consumed, heated, swept away, or kept from cooling into star-forming clouds, the supply of new stars can fall to a trickle. The brightest blue stars disappear first because their lives are brief. Longer-lived, redder stars remain, and over time the galaxy's overall light shifts toward older stellar populations. It may continue shining for an almost unimaginable span of time. What has ended is not light itself, but renewal. Astronomers also classify galaxies by shape, although appearance should never be confused with a simple aging chart. Spiral galaxies contain rotating disks traced by curving arms. Barred spirals carry an elongated concentration of stars across the center, while lenticular galaxies preserve a disk but show little obvious spiral pattern. Elliptical galaxies appear smoother, ranging from nearly round to distinctly stretched. Irregular galaxies refuse the cleaner symmetry of those categories. Dwarf galaxies form their own broad family and can themselves look irregular, elliptical, spheroidal, or like something between the familiar classes. Early in the 20th century, Edwin Hubble helped arrange these forms into the famous classification diagram often called the Hubble tuning fork. Ellipticals occupy one side, while ordinary spirals and barred spirals branch away along separate paths. It is a useful map of appearance, but not a literal family tree. That distinction matters. A diagram does not mean that a spiral naturally grows old and turns into an elliptical as if moving from one box to the next. Nor is an elliptical simply an elderly spiral. Real galaxies can be transformed by many different histories, sometimes gradually and sometimes violently. To understand those histories, we have to leave present-day galaxies behind. We must go earlier than the Milky Way, earlier than Andromeda, earlier than every mature disk and smooth elliptical we see nearby. We must return to a universe before spiral arms, before disks, and before the first star had ever shone. The young universe was remarkably uniform. Yet hidden inside that near uniformity were minute differences from place to place. They were almost unimaginably small, but gravity had an enormous amount of time available. Those tiny imbalances would eventually be amplified into every large structure around us. At that stage there were no galaxies at all. No glowing spirals, no giant ellipticals, no immense galaxy clusters tied together across millions of light years. Matter was spread through space far more evenly than it is today, with only the slightest departures from perfect smoothness. Some regions contained a little more material than average, others a little less. The contrast was tiny, but it did not need to be dramatic. A small excess of matter meant a small excess of gravitational pull, and given enough time, that slight advantage could grow. Those early differences became the starting pattern from which later structure emerged. Modern cosmology describes much of this story with a framework known as the lambda-Cole dark matter model, often shortened to lambda-CDM. The name may sound technical, but its broad outline is surprisingly simple. The universe expands, and its large-scale behavior depends on several major ingredients. One is ordinary matter, the atoms that make stars, planets, dust, and eventually living things. Another is dark matter, invisible to ordinary light, but deeply important because of its gravitational influence. Radiation also mattered greatly in the early universe. And then there is dark energy, the name given to whatever is driving the observed acceleration of cosmic expansion. Within this picture, galaxies are not objects that suddenly switch on. They emerge because very small early differences gradually become larger. But that immediately opens another door. If the first galaxies grew from tiny variations in density, where did those variations come from? One leading explanation reaches back to an extraordinarily early episode called cosmic inflation, a brief interval in which space itself may have expanded at an extreme rate. Physicist Alan Guth was among the key figures who developed the modern inflationary idea in the late 20th century. Inflation was proposed in part to explain why distant regions of the observable universe look so similar, even though, under a simpler history, they appear to separated to have easily exchanged information. Inflation may also help explain the first evidence. Quantum physics tells us that even what seems like empty space is not perfectly quiet. At microscopic scales, fluctuations naturally appear. During a period of rapid expansion, tiny variations like these could have been stretched to enormous dimensions. Something that began at a scale far smaller than an atom could, in principle, leave an imprint across astronomical distances. When inflation ended, those stretched fluctuations would remain as faint differences in the distribution of matter and energy, a barely visible pattern waiting for gravity to amplify it. The real mathematics is far richer than this simple picture, of course, but the central idea is gentle enough to follow. A region with a little more matter pulls slightly harder on its surroundings. That extra pull brings in a little more material, making the region denser still. With more matter comes more gravitational attraction, and with more attraction comes still more matter. At first the difference is almost invisible. Over immense spans of time, however, the advantage accumulates. Meanwhile, regions that began slightly under-dense fall increasingly behind their denser neighbors. Many of those under-dense regions eventually became the immense cosmic voids that fill much of the universe's volume. The denser regions followed the opposite path. They became the sites where galaxies, groups, clusters, and the enormous connecting filaments of the cosmic web would later take shape. And this early pattern is not merely an elegant theory. We can observe an ancient trace of it in the cosmic microwave background. About 380,000 years after the Big Bang, the universe had cooled enough for electrons to join atomic nuclei, allowing mostly neutral hydrogen and helium to form. Before that transition, free electrons scattered photons again and again, making the young universe behave like a glowing fog. Once neutral atoms formed, light could travel much more freely. That ancient light has been crossing space ever since, carrying information from a time long before the first galaxy. As the universe expanded, the wavelength of that radiation stretched until today. It lies mainly in the microwave region of the spectrum. We detect it as the cosmic microwave background, a faint signal arriving from every direction, a distant afterglow from the young universe. Arno Penzias and Robert Wilson encountered this background unexpectedly in the 1960s, while working with a highly sensitive radio antenna. They found a persistent noise that remained no matter how carefully they inspected the instrument. Eventually it became clear that the signal was not local interference at all. It was ancient radiation filling the sky. Later spacecraft mapped that background with far greater precision. A Cosmic Background Explorer, or COBE, provided some of the first convincing measurements showing that the microwave glow was not perfectly uniform from one direction to another. George Smoot became closely associated with measurements of those tiny temperature differences, while John Mather Lead worked demonstrating that the background possessed the nearly perfect thermal spectrum expected from a hot early universe. New missions would soon sharpen the picture even further. The Wilkinson microwave anesotrope probe mapped the fluctuations with much greater detail. Later, the Planck mission improved the measurements again, giving cosmologists extremely precise information about the universe's age, geometry, composition, and the pattern from which later structures would grow. What is most remarkable is not how large those early differences were, but how small. Across the microwave background, temperature variations are only about 1 part in 100,000. The young universe was extraordinarily smooth, yet not so smooth that gravity had nothing to work with. Instead, the sky contains a delicate mottling of slightly warmer and slightly cooler regions. Those variations reflect subtle differences in density and motion. In a sense, the cosmic microwave background is not a picture of galaxies themselves, but a faint blueprint of where the future universe could begin to become uneven. It may seem surprising that such tiny differences could lead to something as dramatic as a galaxy. Yet gravity does not require a spectacular beginning. A region only needs to be slightly denser than its surroundings. Given enough time, that tiny advantage changes the path of nearby matter. Material drifts toward the denser region. A region gains mass, its pull strengthens, and still more material follows. Across hundreds of millions of years, a barely noticeable irregularity can become something enormous. But there was a complication. Ordinary atomic matter could not have built the observed structures quickly enough by itself. For much of the early universe, normal matter was strongly coupled to radiation, which made collapse difficult. If all cosmic structure had waited for ordinary matter alone to begin gathering efficiently after the microwave background was released, galaxies would have struggled to assemble as early as observations show they did. Something else had already begun arranging the gravitational landscape before ordinary gas was free to settle into it. This component did not shine. It did not form familiar atoms. Yet its gravity could gather into structure and prepare the places where visible matter would later collect. That hidden scaffolding was dark matter. It is one of the strangest parts of the galactic story because we still do not know what dark matter is made of. We recognize its influence everywhere, yet no telescope can simply point toward an isolated patch of it and see it below. Dark matter appears not to emit, reflect, or absorb ordinary light in the familiar way. If a clump of it were sitting alone in otherwise empty space, it would give our eyes no obvious signal. Its presence becomes known only when gravity reveals what the invisible mass is doing. We see stars orbiting too rapidly for the visible contents of galaxies to account for. We see galaxies moving through clusters as though far more mass is present than their light suggests. We watch background light bend around massive systems, tracing gravity even where little luminous matter can be found. Again and again, the same conclusion appears: the matter we can see does not provide enough gravity. Nor can the missing mass simply be explained by enormous clouds of ordinary gas, vast populations of faint stars, or dust hidden from view. Multiple independent observations point towards something fundamentally different. Measurements of the cosmic microwave background, the abundance of light elements, gravitational lensing, the behavior of galaxy clusters, and galactic rotation all support the idea of a non-baryonic component, a form of matter, like the atoms built mainly from protons and neutrons. The evidence accumulated gradually rather than appearing in one decisive moment. In the 1930s, astronomer Fritz Zwicky studied the motions of galaxies in the Coma cluster. Because gravity binds a cluster together, the speeds of its galaxies can be used to estimate how much mass must be present. Zwicky found that those galaxies seemed to be moving far too quickly for the visible material alone to hold the cluster together. It was an early indication that a great deal of mass was missing from the luminous picture, an idea that would become far more convincing as new evidence appeared decades later. At the time, the result was suggestive rather than conclusive. The idea of unseen mass had not yet become the modern dark matter picture. But several decades later, another line of evidence would make the problem much harder to ignore, this time by looking at how stars move inside spiral galaxies. Vera Rubin, working with astronomer Kent Ford, measured the orbital speeds of stars and glowing gas at different distances from galactic centers. If most of a galaxy's mass were concentrated where most of its visible light is found, a simple expectation followed: stars farther out should generally orbit more slowly. That is broadly what happens in the solar system. The farther a planet lies from the Sun, the lower its orbital speed tends to be. Yet spiral galaxies did not follow that pattern. Far from their bright centers, stars often continued moving at unexpectedly high speeds. The resulting graphs became famous as flat rotation curves. Instead of orbital speed declining strongly with distance, it often stayed nearly level. One natural explanation was that the bright disk was embedded within a far larger distribution of mass that produced little or no light. Even where starlight became faint, gravity remained strong. This helped establish the idea of extended dark matter halos surrounding galaxies. And these halos were not merely an extra feature added after galaxies formed. In the standard cosmological picture, they were present from very early times. Most dark matter in that picture is described as cold dark matter. The word cold is a technical one here. It does not simply mean chilly. It means the particles moved slowly enough, compared with the expansion of the early universe, for gravity to gather them efficiently into growing concentration. Small concentrations formed first. Over time they merged and became larger. This bottom-up growth is called hierarchical structure formation. Rather than giant clusters and massive galaxies appearing fully assembled at the beginning, smaller dark matter halos generally emerged earlier and then combined into larger ones. Across vast scales, gravity did not arrange these halos as isolated beads scattered randomly through space. A growing universe developed a network along filaments, broad sheets, dense intersections, and enormous empty-looking regions between them. Together this structure is known as the cosmic web. Galaxies would later become especially common along those filaments, on near the dense nodes where several filaments meet. So dark matter did more than add hidden mass to individual galaxies. It helped shape the large-scale geography of the universe itself. Inside this growing web, each dark matter halo created a gravitational basin. Ordinary hydrogen and helium could fall toward it. As more material accumulated, the gravitational well deepened, making it easier for still more matter to remain bound rather than escaping back into intergalactic space. That is why dark matter halos are often treated as the underlying framework of galaxies. A visible galaxy develops within the halo. It is not that a finished disk of stars forms first and later acquires a dark shell around it. The invisible structure is already part of the story from the beginning. A halo should not be pictured as a rigid sphere, however. It changes continuously. It can gain material from its surroundings, collide and merge with other halos, and carry smaller subhalos in orbit. Some of those smaller structures may host dwarf galaxies, others may contain very little visible matter at all. Its mass can grow, its shape can shift, and its motion responds to the gravitational environment around it. In the late 20th century, Simon White and Martin Rees helped develop an influential framework in which galaxy formation unfolds naturally inside these growing dark matter structures. In that picture, dark matter halos form and deepen first. Ordinary gas falls into them, loses energy, cools, and eventually becomes dense enough to build the visible components of a galaxy. The details have changed enormously as observations and simulations have improved, but this broad framework remains central. Modern simulations try to follow dark matter and ordinary matter at the same time. Dark matter is comparatively straightforward in the standard model because its dominant effect is gravity, and it rarely collides with itself in the ordinary sense. Gas, by comparison, behaves in a far more complicated way. Gas has pressure. It can heat and cool. It becomes turbulent, compresses into clouds, forms stars, absorbs and emits radiation, gains heavy elements from stellar evolution, and can be blasted outward by supernova or by activity around massive black holes. Each process affects the others. So a realistic simulation of a galaxy must connect physical events occurring on radically different scales. And even after decades of evidence for dark matter's gravitational role, one mystery remains untouched. We still do not know the identity of the dark matter particle itself. Weakly interacting massive particles, often called WIMPs, were long among the leading candidates. Axions are another major possibility, and many other models propose additional particles or even hidden sectors of physics. So far, no candidate has been confirmed as the substance responsible for cosmic dark matter. That leaves dark matter in a peculiar scientific position. Its gravitational fingerprints appear across the universe, while the thing leaving those fingerprints remains unidentified. Yet for galaxy formation, its role seems fundamental. Before the first stars or galaxies became visible, dark matter was already connecting into halos. Those halos became deeper gravitational wells, and ordinary hydrogen and helium began to fall inward. Unlike dark matter, gas could collide with itself, turn motion into heat, radiate some of that energy away, and slowly become denser. When enough gas finally cooled and collapsed, the darkness would no longer remain complete. The first stars were approaching. After the cosmic microwave background was released, the universe entered a long interval with matter everywhere but almost no starlight anywhere. Hydrogen and helium filled space. Dark matter continued assembling, and the luminous universe familiar to us had not yet switched on. Astronomers call this interval the cosmic dark ages. It began after the universe became transparent, about 380,000 years after the Big Bang, and lasted until the earliest stars appeared. During this long twilight, ordinary gas was slowly falling into dark matter halos that had already started to grow. As hydrogen and helium accumulated in those gravitational wells, the gas became compressed. Compression raised its density, but gravity still needed help. For the gas to contract further, it had to lose some of its thermal energy. Cooling was therefore one of the key steps toward the first stars. Today, star-forming clouds contain carbon, oxygen, dust grains, and many other ingredients that help gas radiate energy efficiently. The early universe had none of that richness. It was composed almost entirely of hydrogen and helium, with only tiny traces of a few other light elements. One important cooling route involved molecular hydrogen. When two hydrogen atoms become bound together, the resulting molecule can help carry thermal energy away from dense gas. Even in the chemically simple early universe, small amounts of molecular hydrogen could form inside sufficiently compressed regions. As those molecules radiated energy, the gas cooled. With lower temperature came lower pressure, and pressure became less effective at resisting gravitational collapse. Dense pockets contracted further until some reached the conditions needed to begin producing the first generation of stars. Astronomers usually call that hypothetical first-generation population II stars. The numbering feels backward only because the older naming system was created from stars observed later. Population I includes stars like the Sun, while population II generally refers to older stars with fewer heavy elements. Population II reaches farther back, to stars born before earlier stellar generations had enriched the cosmos with large amounts of carbon, oxygen, iron, and other heavy elements. These stars should therefore have formed from material made almost entirely of hydrogen and helium. No individual population II star has yet been securely identified. But the idea is not merely a decorative possibility. The universe began with almost no heavy elements, while later generations clearly contained them. Those elements had to be forged and dispersed by stars that came before. Carbon, oxygen, Silicon, iron, and many other elements could not simply appear without a history. So some early generation of chemically primitive stars must have existed. Their exact properties remain an active research problem, but their role in cosmic evolution is difficult to avoid. Many simulations suggest that at least some of the first stars may have grown much more massive than stars commonly forming in the Milky Way today. With almost no metals or dust, primordial gas cooled in a different way, and that may have favored the formation of larger collapsing fragments. Larger fragments could, in turn, produce more massive stars. And it would be too simple to imagine every first-generation star as an enormous giant. A full range of their masses remains uncertain. What matters most is what happened once some of those first stars finally began to shine. Massive young stars poured ultraviolet radiation into their surroundings, heating nearby gas and changing its chemistry. Stellar winds pushed material outward, and because massive stars spend their nuclear fuel quickly, some lived only a short cosmic moment before ending in powerful supernova explosions. Those explosions changed more than the local neighborhood. Nuclear reactions inside stars had already been building heavier elements, and stellar death added and dispersed more. When supernova debris mixed with surrounding gas, the chemical simplicity of the early universe began to disappear. Carbon became more common. So did oxygen, silicon, iron, and other ingredients that would one day become part of rocks, atmospheres, oceans, planets, and living chemistry. But the first galaxies carrying these stars did not yet resemble the elegant spirals we see in nearby space. They were small, restless, and irregular. Gas rushed inward, star formation came in uneven bursts, supernova threw material back out, and dark matter halos repeatedly merged. Young proto-galaxies collided and combined, changing shape again and again, as if the universe were still sketching and erasing their outlines. Rather than finished islands of starlight, these early galaxies were closer to luminous works in progress. Their radiation also helped drive one of the great transitions in cosmic history, reionization, when much of the neutral hydrogen between galaxies became electrically ionized once again. After the cosmic microwave background was released, most intergalactic hydrogen had become neutral. Later, energetic ultraviolet photons began stripping electrons away from hydrogen atoms. Over hundreds of millions of years, expanding regions of ionized gas spread through the space between young galaxies. Hot, massive stars inside early galaxies probably supplied a large fraction of the required ultraviolet radiation. Very faint galaxies may have mattered greatly simply because they were so numerous, but are still working out how much each population contributed to the transformation. Accreting black holes may also have added energetic radiation. Another uncertainty is how easily ionizing photons escaped from young galaxies through their own gas and dust. The answer determines how effectively those galaxies could influence the wider universe beyond their immediate surroundings. This distant era is now being studied with a level of detail that was impossible only a short time ago. The James Webb Space Telescope was designed in part to observe the early universe, especially at infrared wavelengths where light from very distant galaxies has been shifted by cosmic expansion. Because space has been expanding while the light travels, wavelengths from remote galaxies are stretched toward the red end of the spectrum and beyond. This is redshift. In general, the farther away we look, the farther back in cosmic history the arriving light allows us to see. Light has a finite speed, so when a telescope detects a galaxy more than 13 billion light-years away, it is not seeing that galaxy as it might exist today. It is receiving photons that began their journey when the universe itself was only a small fraction of its current age. This connection between distance and history is often called look-back time. It allows astronomers to study phases of galaxy formation that vanished billions of years ago. Webb has revealed unexpectedly bright and apparently developed galaxies from within the first few 100 million years of cosmic history. Some appear to have built up stellar mass faster than earlier models anticipated. That does not mean the standard cosmological framework has simply collapsed. Instead, the observations create useful pressure on the details, forcing astronomers to ask how efficiently early galaxies could gather gas and turn it into stars. Models must also account for how quickly dust formed, how feedback operated, and how young galaxies grew inside their dark matter halos. By now, the universe had changed enormously. Where once there had been no stars, stellar light was becoming common and chemically enriched gas was spreading outward. Supernovae were manufacturing and dispersing heavy elements. Young galaxies poured radiation into surrounding space. Gas was heated, cooled, expelled, mixed, and pulled back inward. Gravity had transformed barely visible early density differences into genuine luminous systems. Yet these galaxies were still relatively small. To grow into the giant systems seen later, they needed a continuing supply of material. Their dark matter halos had to keep gaining mass, and ordinary gas had to keep arriving. Over time, the chaotic early systems would begin developing more persistent structures, including rotating disks. A young galaxy cannot grow on the stars it already contains. It needs fresh, ordinary matter. Much of that material comes from the cosmic web, where gas follows the same immense filaments that connect galaxy groups and clusters across distances far beyond the size of any single galaxy. A dark matter halo therefore lives inside a larger network rather than in isolation. Gravity continually draws material toward it. Some incoming gas can remain relatively cool, while other gas is heated strongly as it falls inward and encounters material already surrounding the growing galaxy. When rapidly moving gas meets denser gas, shock waves can form. Some of the motion is converted into heat, raising temperatures to hundreds of thousands or even millions of degrees. So the region around a galaxy can contain matter in many very different thermal states at the same time. Astronomers refer to much of this extended reservoir as the circumgalactic medium, or CGM. It surrounds the bright stellar galaxy and reaches far beyond the visible disk. Although it may appear empty in ordinary images, it is a dynamic part of the galaxy's life. A circumgalactic medium can contain hot plasma, cooler clouds, newly arriving intergalactic gas, and chemically enriched material previously thrown outward by stars. It is less like empty space and more like a vast exchange zone between a galaxy and the larger cosmic environment around it. Gas can move inward from this reservoir and feed future star formation. It can also be driven outward into it by stellar winds, supernovae, or energetic activity near a central black hole. Some expelled matter escapes, some cools and returns later, beginning another cycle. For gas to move deeper into a halo and help build the visible galaxy, it generally has to lose energy. One important mechanism is radiative cooling. Hot gas contains rapidly moving particles, and interactions among them can allow energy to leave in the form of electromagnetic radiation. As the gas cools, pressure provides less support against gravity. A material can sink inward. Yet it does not usually fall straight toward the center like rain toward the ground. Almost all incoming matter carries some angular momentum, meaning it has sideways motion as well as inward motion. Even a modest amount of sideways motion becomes important as a cloud contracts. A useful analogy is a skater pulling their arms closer to the body. As the skater becomes more compact, rotation speeds up. Collapsing gas behaves in a broadly similar way while approximately conserving angular momentum. The closer the material moves toward the galactic center, the more important its rotation can become. Instead of all the gas piling into one point, much of it settles into orbit. Collisions among gas clouds also redistribute energy and angular momentum while allowing some motion to be radiated away. Over time, this combination of gravity, cooling, collisions, and rotation can flatten the gas into a broad disk. The process is neither perfectly smooth nor identical in every galaxy, but it provides one of the main routes by which the familiar luminous disks of spiral galaxies can emerge. Dark matter follows a different path. In the standard picture, it does not interact electromagnetically in the way ordinary gas does. It cannot efficiently radiate heat, collide into dense cooling clouds, and settle into a thin rotating layer. Instead, it remains spread through a much broader halo. Because dark matter cannot shed energy the way gas can, it stays distributed through a deep, extended halo, while ordinary matter settles into a much thinner luminous disk. Yet those first galactic disks were probably nothing like the calm, graceful spirals we often see in nearby photographs. Young disks could be thick, turbulent, and uneven. Huge clumps of dense gas might from inside them, sometimes producing stars at extraordinary rates. Fresh material arrived from different directions, constantly disturbing the motion of gas that had only recently begun to organize itself. Our young galaxy might also endure repeated mergers with smaller systems. Each encounter could add stars, gas, and angular momentum while disturbing whatever order had already developed. Even a mature disk is not one simple layer, but a collection of distinct structures built over time. The thin stellar disk contains much of the younger population and much of the cold gas where star formation continues today. A thicker disk reaches farther above and below the galactic plane and generally contains older stars whose orbits are less tightly ordered. Near the center, many disk galaxies contain a bulge, a dense concentration of stars that may have formed through early collapse, mergers, or slower internal rearrangement. Beyond the bright disk lies a diffuse stellar halo containing ancient stars, globular clusters, and debris from smaller galaxies absorbed long ago. These parts do not appear according to one fixed timetable. Our galaxy can be built, disturbed, and partially rebuilt many times. A minor merger can thicken a disk by giving stars more random motion, while a passing satellite can tug on the disk and bend or warp its structure. Incoming gas may also arrive with its rotation tilted relative to material already present. Gravitational torques can move angular momentum from one region to another. Internal instabilities can create bars, rings, or dense central concentrations, even when no external collision is taking place. Sometimes an existing disk is badly disturbed. Later, fresh gas may settle into orbit and help build another. Disk formation, then, is not a single event that happens once and remains complete. It is an extended process that may continue for billions of years. For most of its life, a galaxy remains connected to its surroundings. Matter enters and leaves. Gas cools and heats. Orbits shift. The visible disk we see at any one moment is simply the current arrangement produced by everything that happened before. And once enough cool gas settles there, gravity begins concentrating it further. Dense clouds appear. Smaller regions inside them grow older and more compact. Some collapse far enough for protostars to form and eventually ignite. Those stars then return both energy and material to the environment around them, continuing the cycle that shaped their own birth. Some stars end as supernova, heating and enriching nearby gas. Some of that gas is expelled, some remains, and some eventually cools and falls back. Over cosmic time, a galaxy builds itself through this constant circulation of matter between gravity, radiation, stellar life, and motion. Deep inside a disk, stars form mainly in the coldest and densest parts of molecular clouds. These enormous clouds are cool enough for molecules to survive and dense enough for gravity to begin gathering smaller pockets of material into still tighter structures. A molecular cloud is anything but still. Gas moves through it. Turbulence creates knots on filaments. Magnetic fields provide support, and internal pressure resists collapse. Yet in some places gravity slowly gains the advantage, drawing the densest regions inward. Those dense cores contract, becoming still denser until some develop into protostars. This is why a galaxy can contain enormous amounts of gas without forming stars everywhere at once. Only part of that gas reaches the cold, dense state required for efficient collapse. Much of the remaining gas may be too warm, too diffuse, or too turbulent. Observationally, astronomers have found a broad connection between how much gas is packed into a region and how rapidly that region tends to form stars. This relationship is known as the Kennickett-Schmidt relation, named for Robert Kennickett and Martin Schmidt. In general, regions with greater gas surface density form stars more rapidly. It is not a perfect law for every cloud or every galaxy, but it captures an important tendency. Dense gas makes star formation easier, yet the moment stars appear, they begin altering the conditions around them. The most massive young stars have an especially strong influence because they radiate intensely, particularly in ultraviolet light. That radiation heats and ionizes nearby gas. Powerful stellar winds push material outward at high speeds, and because massive stars use their nuclear fuel quickly, some survive only a few million years before ending in enormous supernova explosions. Together, these effects inject energy and momentum into the interstellar medium. Astronomers call the combined process stellar feedback. Feedback can slow further star formation by disrupting the same dense clouds from which the stars recently emerged. Radiation and winds carve cavities through gas. Supernova shocks can tear molecular clouds apart, scattering and heating material that might otherwise have formed more stars. But feedback is not purely a break. In another place, the same shock wave can squeeze gas rather than disperse it. If that compressed gas becomes dense enough, gravity can take over and trigger a new collapse. One generation of stars can therefore suppress star formation in one region while encouraging it in another. Galaxies regulate themselves through this complicated balance between collapse and disruption. The effects can reach well beyond individual star-forming clouds. When many supernovae occur across a galactic disk, some gas can be heated so strongly that it rises thousands of light years above the plane, carrying energy and chemically enriched material with it. This circulation can form what astronomers call a galactic fountain. Hot gas flows upward into the halo, expands, and gradually cools. Some may later lose enough energy to fall back toward the disk. It has not necessarily escaped the galaxy. It has simply taken a long route away and back again. In dwarf galaxies, the outcome can be more severe. Their gravitational wells are relatively shallow, so an energetic burst of stellar feedback may push gas outward strongly enough for some of it to escape altogether. In small galaxies, losing gas can dramatically limit future growth. This makes supernova and stellar winds especially important in low-mass systems. At the same time, dying stars are performing another transformation just as important. They are changing the chemical composition of the galaxy itself. The early universe contained almost nothing beyond hydrogen, helium, and traces of a few light elements. Inside stars, nuclear fusion builds heavier nuclei. Massive stars produce carbon, oxygen, neon, magnesium, silicon, and other elements through different stages of their lives. Supernova create and disperse additional elements, while other stellar processes contribute still more. With each generation, the gas between stars becomes chemically richer. Astronomers use the word metals for every element heavier than helium, even when that sounds strange by everyday chemistry standards. So oxygen, for example, counts as a metal in astronomical language. As galaxies evolve, their stars and gas generally become more enriched in these heavier elements. This enrichment changes how later generations of stars form, because it allows dust grains and more efficient cooling to become increasingly important. Dust can help shield molecules from energetic radiation, provide surfaces for chemical reactions, and allow gas to cool more effectively. Eventually, some of those same grains become ingredients in planetary systems. Galactic evolution therefore reaches all the way forward to the material from which worlds can be built. Rocky planets depend on silicon, magnesium, oxygen, iron, and many other elements that were nearly absent in the early universe. Carbon-based chemistry requires atoms that had to be manufactured inside stars before they could become part of planets, oceans, rocks, atmospheres, and living organisms. In that sense, a galaxy is not only a machine for making stars, it is a vast recycling system. Gas forms stars. Stars alter the gas. Some stars die and return enriched material to space. That material cools, mixes, and becomes available to the generations that follow. Inside a rotating galactic disk, young stars are rarely spread perfectly evenly. Many of the brightest gather along immense curving regions, extending across thousands of light years. From a distance, these concentrations of gas, dust, and new stars trace the spiral arms that make some galaxies so recognizable. A spiral galaxy can look almost sculpted, with luminous arms sweeping away from a central bulge and winding through a broad stellar disk. Yet the beauty of the pattern can be misleading. The arms are not solid lanes made from the same stars forever. The entire galaxy rotates. Individual stars follow their own orbits, and gas clouds move through the disk as well. A spiral pattern can remain visible even while much of the material that makes the pattern bright is constantly entering and leaving different parts of it. That distinction leads to a classic puzzle known as the winding problem. Material near the center of a spiral galaxy generally completes an orbit more quickly than material farther out. If the arms were simply permanent rows of stars, they should not keep their familiar open shape for long. The inner portions would move ahead while the outer portions lagged behind. With every rotation, the arms would become more tightly wrapped around the center. After enough time, the broad spirals seen in many galaxies should have wound themselves into an extremely tight pattern. But prominent spiral structure has persisted in many galaxies for billions of years, so something subtler must be happening. One influential explanation is density wave theory, developed mathematically in the 20th century by C. Lin and Frank Xu. In this picture, a spiral arm can behave as a region of enhanced density moving through the disk. The stars themselves are not necessarily trapped inside that arm for their entire orbit. Instead, stars and gas can enter a denser region, pass through it, and later emerge again. A useful comparison is a slow-moving patch of traffic on a highway. The congestion may remain recognizable for some time even though the individual cars inside it are constantly changing. Cars enter, move through, and leave, while the traffic pattern itself persists. Spiral arms can behave in a roughly similar way. Stars may pass through while the broader density pattern survives. Gas responds even more strongly because it can be compressed as it enters a denser region, and gas clouds can collide or gather additional material there. That compression makes it easier for some gas to cool and become dense enough to collapse. New stars can then form along the arm. The most massive of these newborn stars are exceptionally hot and luminous, especially at blue and ultraviolet wavelengths. As a result, many spiral arms appear distinctly blue in astronomical images. The blue light does not mean that most of the galaxy's stars live permanently inside the arms. Older stars are spread throughout the disk. The arms simply become highly visible wherever young, bright stars are concentrated. Gas and dust also collect there, reinforcing the pattern. Density wave theory explains some spiral structures well, but galaxies do not all display the same kind of arms, and no single mechanism accounts for every spiral seen in the universe. Some galaxies show to broad, dominant arms winding around much of the disk. Others have many shorter, broken segments. The latter are often called flocculent spirals because their structure looks patchy, or less orderly than a ground design spiral. Local gravitational instabilities can help create these shorter features. A slightly overdense region attracts more material, strengthening its own gravitational influence. Temporary spiral segments can appear, fade, and later form again somewhere else in the disk. Computer simulations suggest that some spiral structure may therefore be recurrent, rather than permanent, a pattern that repeatedly reorganizes itself instead of one wave surviving unchanged for the entire history of a galaxy. Nearby galaxies can also help. A close gravitational encounter pulls unequally on different parts of a disk, creating tidal distortions that may stretch into prominent spiral arms. In some systems, the shape we admire is partly the lingering imprint of a neighbor's gravity. A whirlpool galaxy is a famous example. Its smaller companion has interacted gravitationally with the larger spiral, and that encounter is thought to have strengthened the whirlpool's dramatic arm structure. The beauty of the pattern is therefore connected to a long gravitational conversation between two galaxies. So spiral arms can arise in several ways. Long-lived density patterns may contribute. Temporary instabilities may contribute. External tidal encounters may contribute. In many real galaxies, more than one mechanism may be operating at the same time. Some spiral galaxies contain another striking structure crossing their centers, a galactic bar. A bar is an elongated concentration of stars extending through the inner disk. It may look simple in an image, but dynamically it can influence the entire galaxy around it. Bars exchange angular momentum with stars, gas, and other parts of the galaxy. Their gravitational pull can guide gas away from wider circular orbits and gradually funnel some of it inward toward the central regions. That inward flow can help produce dense rings where new stars form, and it may also affect how much material reaches the neighborhood of a central supermassive black hole. Our own Milky Way is a barred spiral, with a stellar disk roughly 100,000 light-years across. The galaxy's faint outer regions extend even farther. Yet mapping the Milky Way's exact spiral pattern is surprisingly difficult because we live inside the disk. We cannot step outside the galaxy, rise above it, and take a clean photograph from a distance. Instead, astronomers reconstruct the structure from measurements of stars, gas clouds, radio emission, distances, and motions. Several major arms and smaller features have been identified, though the exact arrangement continues to be refined as better observations become available. From somewhere far beyond the Milky Way, our galaxy would probably look simpler than it feels from within. A broad luminous disk, a central bar, and curving regions of gas and young stars. Yet even that familiar shape is temporary when viewed on cosmic dimescals. Gas can be lost. Disks can thicken. Encounters can disturb billions of stellar orbits. Some galaxies eventually show little obvious spiral structure at all. As ordered rotation becomes less visually dominant, a disk can give way to something smoother, rounder, and very different. This is why galaxy categories are useful but never perfect. Terms such as spiral, elliptical, lenticular, and irregular help astronomers organize the immense variety of forms in the universe, but real galaxies often sit between the clean examples shown in textbooks. One spiral may have a large central bulge, another a small one. Some carry strong bars, others none. Some disks remain rich in cold, gas-and blue young stars, while others are smoother and quieter. The same broad label can hide very different histories. The central bulge is one of the most important structures in many disk galaxies. A classical bulge is a dense, roughly rounded concentration of stars. Its stars tend to move on a wider range of orbits than those in the thin disk, where rotation is much more ordered. Classical bulges often contain older populations and can resemble small elliptical galaxies embedded inside larger disks. Yet not every bulge forms the same way. Some galaxies contain so-called pseudo-bulges, structures that remain more closely connected to the surrounding disk. Pseudo-bulges tend to be flatter, may rotate more strongly, can contain appreciable gas, and sometimes continue forming stars. Rather than being built mainly by an ancient major merger, a pseudo-bulge can emerge gradually as material in the disk is rearranged over billions of years. A galactic bar can drive much of that slow rearrangement. Bars can arise when a rotating stellar disk develops a large-scale instability. Many stellar orbits become aligned in a way that produces an elongated feature through the inner galaxy rather than a purely circular distribution. Once present, a bar can reshape the disk for a very long time. It interacts gravitationally with stars, gas and surrounding dark matter halo. Through those interactions, angular momentum can move from one part of the galaxy to another. Gas responds especially strongly because it can collide, lose energy, and change its orbit. A bar can therefore channel gas inward, away from the outer disk and toward the central region, where conditions may become quite different from those farther out. Some of that gas collects in rings and becomes dense enough to form new stars. Some may travel still farther inward toward the surroundings of the central supermassive black hole. A galaxy can therefore change substantially even without colliding with another large galaxy. Astronomers call this kind of slow, internally driven change secular evolution. Here, secular simply means gradual evolution over long periods, rather than a sudden transformation caused by a major external event. Bars grow or weaken. Gas migrates inward. Stellar orbits shift. Central regions become denser. Spiral patterns can fade. Over billions of years, these modest changes can alter a galaxy's appearance considerably even if no dramatic merger occurs. Some galaxies occupy an especially clear middle ground between spirals and ellipticals. These are lenticular galaxies. They contain a flattened disk and usually a central bulge, much like spirals, but they show little obvious spiral structure. Lenticular rests also tend to contain less cold gas and form fewer new stars than active spirals. Seen from far away, one may look like a smooth, glowing lens. Yet there is no single agreed path by which every lenticular galaxy came to look that way. Some may once have been spirals that slowly lost or consumed their cold gas. Others may have had gas stripped away by the surrounding environment. Minor mergers can thicken a disk without completely destroying it, and repeated encounters can make stellar orbits less orderly. When star formation declines, the bright young stars that once outlined spiral arms disappear. Without those luminous markers, the patterns themselves can become difficult to see. A galaxy may therefore look smoother even without experiencing one spectacular collision. During the 20th century, astronomer Gira Divokulas expanded galaxy classification beyond the original Hubble sequence, recognizing a much wider variety of intermediate forms, bars, rings, and spiral structures. The added complexity reflected something important about galactic evolution. Morphology tells us what a galaxy looks like now. It does not automatically reveal how it arrived there. Two galaxies with nearly identical shapes may have followed very different histories. One may have grown quietly while continuing to draw gas from its surroundings. Another may have lost gas inside a crowded cluster. A third may have absorbed several smaller companions. A fourth may have been reshaped mostly by its own bar and internal gravitational instabilities. Accretion, feedback, environment, mergers, and internal evolution can all leave similar-looking results. So galaxies are less like objects permanently assigned to one category and more like systems whose present shape records only part of a long history. Some retain elegant rotating disks. Some lose the visible spiral pattern while keeping the disk itself. Others become much rounder, with stars moving along many different kinds of orbits and little evidence of the ordered rotation typical of a thin disk. And this leads to a larger question: if slow internal evolution can change a spiral only so much, what creates the giant smooth ellipticals seen throughout the universe? Elliptical galaxies can include some of the largest galaxies known. They look very different from the thin disks and sweeping arms that often come to mind when we picture a galaxy. Instead, their light is smooth, and their overall shape may be nearly round or noticeably elongated. The stars move in many directions rather than sharing one dominant thin rotating plane. Some ellipticals do rotate overall, but the organized disk-like motion is usually much less important than the broad range of stellar orbits supporting the system. Elliptical galaxies also span a huge range of sizes. Some are relatively compact. Others are immense systems containing enormous stellar populations. The largest often sit near the centers of galaxy groups or clusters, where they have had access to a long history of interactions and mergers. Our stars can extend across hundreds of thousands of light years, with faint outer envelopes gradually blending into the surrounding cluster. Strangely, despite their scale and complicated histories, giant elliptical galaxies often look remarkably calm when seen in visible light. Their light is spread smoothly rather than tracing obvious spiral arms. They usually contain less cold molecular gas than actively star-forming spirals, and their average stellar populations are older. With less cold gas available for collapse, many ellipticals create relatively few new stars today. That gives them an overall redder color because the short-lived blue stars associated with recent star formation have mostly disappeared. It might be tempting to imagine that ellipticals simply formed early and then spent the rest of cosmic history unchanged. Their true stories are usually much more complicated. One important route toward an elliptical shape is a major merger, an encounter between two galaxies of broadly similar mass. If both begin with stellar disks, the changing gravitational field of the interaction can severely disrupt the organized structure of those disks. As the galaxies pass through and around one another, stars that once followed relatively orderly orbits can be redirected onto very different paths. After the encounter finally settles, the combined system may be much rounder than either original galaxy. Instead of being supported mainly by one coherent rotating disk, the remnant may be held together by stars moving along a broad range of orbits. A process known as violent relaxation helps redistribute stellar energies during this transformation. The name is dramatic, but the stars themselves are not usually crushing together. Violent relaxation refers to what happens when the galaxy's overall gravitational potential changes rapidly during collapse or merger. A star moving through that changing field can gain or lose orbital energy, and across billions of stars the old ordered pattern becomes increasingly scrambled. The final system can become smoother and more pressure supported. This distinction is important because direct collisions between individual stars are extraordinarily rare during a galaxy merger. Galaxies may contain hundreds of billions of stars, but the distances separating those stars are enormous. Even while the galaxies overlap almost completely, most stars simply pass through the encounter without striking another star. But galaxies collide mainly through their changing gravitational fields. Gas, however, behaves very differently because clouds of gas can physically interact. Gas clouds can collide, compress, radiate energy, and lose angular momentum. During a gas-rich merger, some material is driven toward the center while other regions are squeezed into unusually dense clouds. Under the right conditions, the result can be a sudden rise in star formation. Astronomers call such an episode a starburst. Large amounts of cold gas may rapidly turn into new stars, while some material is funneled toward the central supermassive black holes. A merger can therefore make a galaxy intensely active for a time before gas is consumed, heated, or pushed away. But there is no universal recipe. Not every major merger produces a giant elliptical, and not every elliptical was created by one dramatic collision between two spirals. Some systems have been assembled through a long series of smaller events rather than one defining encounter. Repeated minor mergers can slowly add stars over billions of years. Other galaxies may have built much of their central structure early through rapid, gas-rich collapse. The environment surrounding a galaxy also changes what kinds of encounters and gas supplies are available to it. A galaxy near the crowded center of a massive group or cluster experiences a very different life from one drifting in a quieter region. For the largest ellipticals, growth may continue long after significant star formation has faded, through encounters known as dry mergers. A dry merger involves galaxies containing relatively little cold gas, with little material available for compression into new stars. The collision mainly combines stellar populations that already exist. A galaxy grows larger without producing a spectacular new burst of star formation. Repeated dry mergers can gradually build enormous central galaxies while leaving their stars old and comparatively quiet. To study the mass and internal structure of these systems, astronomers often measure something called stellar velocity dispersion. Rather than asking only how fast the whole galaxy rotates, they examine the spread of stellar speeds toward and away from us. A high-velocity dispersion means that stars occupy a broad range of orbital velocities, reflecting the strength of the gravitational field holding the galaxy together. Those motions help astronomers estimate the mass of an elliptical and compare its hidden gravitational structure with its visible light. So the smooth appearance of an elliptical can hide a surprisingly eventful past mergers, gas loss, starbursts, internal rearrangement, and slow growth layered over billions of years. Some ellipticals rank among the largest stellar systems in existence, yet they are not the most numerous galaxies in the universe. Much smaller systems are far more common, and those modest galaxies may preserve some of the clearest evidence for how larger galaxies assembled in the first place. Dwarf galaxies are faint enough to be easily overlooked beside giant spirals and ellipticals, but their importance is out of proportion to their size. Depending on the type, a dwarf may contain only thousands or millions of stars, while larger dwarfs can hold several billion. That is still small beside a galaxy like the Milky Way, with hundreds of billions of stars. Yet hierarchical formation predicts that small structures generally appeared early and repeatedly combined. In that sense, dwarf-sized systems are not side characters in galactic history, they are part of its foundation. Dark matter halos merged, gas collected inside them, and small stellar systems formed. Many of those early systems were later absorbed into larger galaxies. The Milky Way therefore did not emerge as one enormous finished object. Part of it was assembled from smaller galaxies added over cosmic time. The evidence for that process still survives in the outskirts of large galaxies. Some dwarf galaxies remain rich in gas and continue forming stars. These are often classified as dwarf irregulars because their stars and gas do not settle into the graceful symmetry of a large spiral. Instead, bright star-forming regions may be scattered unevenly across them. The Large Magellanic Cloud, one of the Milky Way's nearby companions, is a familiar example. It contains substantial gas and continues forming stars in active regions, such as the Tarantula Nebula. Other dwarfs are much quieter. Dwarf spheroidal galaxies are generally faint, diffuse, and poor in cold gas. Their light is dominated by older stars, and many are found as satellites orbiting much larger galaxies. Several such systems surround the Milky Way. Their visible stellar populations can be very small, yet the motions of those stars often imply far more mass than the light alone can explain. This makes dwarf spheroids especially valuable for studying dark matter on scales far smaller than giant galaxies or clusters. In some of the faintest known dwarfs, the inferred dark matter mass appears to outweigh the stellar mass by a very large factor. Astronomers estimate this by measuring how rapidly stars move within the galaxy and asking how much gravity is required to keep them bound. If the stars move too quickly for visible matter alone to hold the system together, an additional gravitational component is needed. Dark matter remains the leading explanation. These small galaxies therefore function as natural laboratories for testing how invisible matter behaves. Their small size also makes them unusually vulnerable to stellar feedback. A massive galaxy has a deep gravitational well, so gas driven away from the disk may still remain bound. A dwarf has far less gravitational pull, and energetic events can change its future much more dramatically. If several massive stars explode within a relatively short interval, the combined energy can heat and accelerate large quantities of gas. Some material may be pushed into the outer halo, while some can escape the dwarf entirely, removing fuel that might otherwise have formed later generations of stars. The early universe created another challenge for small galaxies. During cosmic reionization, ultraviolet radiation spread through intergalactic space and heated much of the surrounding gas. In the smallest dark matter halos, gravity may not have been strong enough to retain that heated material efficiently. Gas could be prevented from falling inward or pushed outward before many stars had time to form. Some small halos may therefore have remained almost completely dark gravitational structures containing dark matter but very little visible starlight. This idea connects to a long-standing puzzle known as the missing satellites problem. Simulations built on cold dark matter predict that a galaxy-sized halo should contain many smaller subhalos orbiting within it, far more than the number of bright satellites astronomers once observed around the Milky Way. For a time, that difference looked like a serious tension between simulations and observations. But the picture has become more complicated. Modern sky surveys have discovered many extremely faint satellite galaxies that older telescopes simply could not see. Some contain so few stars that separating their members from ordinary Milky Way for ground stars is difficult. At the same time, theorists have become increasingly aware that a dark matter subhalo does not automatically have to produce a visible galaxy. Ionization, stellar feedback, and inefficient gas cooling can all suppress star formation in very small halos. So the Milky Way may be surrounded by many subhalos that contain little or no starlight at all, leaving their presence to be inferred indirectly through gravity. Two of the most prominent visible satellites are the Large and Small Magellanic Cloud. They are not merely quiet companions drifting beside the Milky Way. Their gravity affects our galaxy. They interact with one another, and large amounts of associated gas stretch across the sky. One of those gaseous structures is the Magellanic Stream. The Large Magellanic Cloud is massive enough that astronomers must include its gravitational influence when modeling the motion of the Milky Way itself. Other dwarf companions have experienced far more destructive encounters with their hosts. A satellite passing close to a larger galaxy feels tidal forces because gravity is slightly stronger on the near side than on the far side. Repeated over many orbits, that difference can stretch the smaller galaxy, peel away outer stars, and remove gas. Eventually, the satellite can be disturbed so severely that it no longer survives as a distinct galaxy. Its stars do not vanish. Instead, they spread into long tidal streams, faint ribbons that preserve the path and memory of a system that once existed independently. With enough time, those streams become more diffuse and blend into the stellar halo of the larger galaxy. In this quiet way, small galaxies help construct large ones, even as they lose their own identities. Some satellites survive for billions of years. Others are gradually absorbed almost completely. Scale the same process upward, and the distinction between a satellite being consumed into large galaxies colliding begins to blur. Gravity does not care whether an encounter looks gentle or dramatic to us. Given enough time, the interaction can reshape both systems involved. The first image to discard when thinking about a galaxy collision is billions of stars smashing together. That is almost never what happens. Stars are tiny compared with the distances between them, so even when entire galaxies overlap, most individual stars simply continue through vast regions of empty space. The scale is difficult to picture. A star can be millions of kilometers across while its nearest stellar neighbor may lie tens of trillions of kilometers away. A galactic collision is therefore not a crash in the everyday sense. It is a vast gravitational rearrangement. Dark matter halos overlap. Stellar populations pass through one another. Gas reservoirs collide and compress. Thus disturbed, magnetic fields become tangled, and the supermassive black holes near the two galactic centers continue moving with the dense central regions around them. The most dramatic visible features often come from tidal forces. Gravity does not pull equally on every part of a galaxy. The near side of an approaching galaxy feels a slightly stronger attraction than the far side, and across ends of thousands of light years the difference becomes important. Stars and gas can be drawn outward into long tidal tails. Bridges of material may form between the two galaxies. Other encounters produce shells, loops, rings, and streams reaching far beyond the original disks, creating structures that can remain visible for hundreds of millions of years. These faint features can outlast the most chaotic stage of the interaction, preserving evidence long after the galaxies have changed shape, and the systems do not usually meet once and immediately settle together. Often they pass one another several times before finally merging. After an initial close passage, their motion may carry them apart again before gravity turns them back toward one another. A process called dynamical friction gradually reduces the orbit. Subramanian Chandrasekhar developed an influential mathematical treatment of this effect. As a galaxy moves through surrounding stars and dark matter, its gravity creates a slight overdensity behind its gravitational wake. That wake pulls backward on the moving galaxy, slowly removing orbital energy and angular momentum. The orbit shrinks little by little. Each passage can bring the galactic centers closer until the two systems finally combine. What happens next depends strongly on their relative masses. In a major merger, both galaxies are large enough to transform one another. Their disks may be heavily distorted or destroyed, stellar orbits scrambled, and the remnant may bear little resemblance to either original galaxy. A minor merger is more unequal. One large galaxy remains dominant while a much smaller companion is gradually absorbed. A smaller galaxy may be stretched apart, stripped of stars and gas, and mixed into the larger system while the host keeps more of its original structure. Once again, gas behaves differently from stars. Most stars pass one another without touching, while gas clouds can collide directly. Gas can shock compress and lose orbital energy. Gravitational torques can also remove angular momentum, allowing some material to flow inward toward the central regions. Under favorable conditions, this concentration of gas can trigger a burst of new star formation. A starburst is simply a period when stars form at an unusually high rate. Large quantities of gas are squeezed into dense clouds, and the rate of stellar birth can rise dramatically compared with the same galaxies before the encounter. But a merger does not guarantee a starburst. The amount of available gas matters, as do the angles and speeds of the encounter, the timing of close passages, and the strength of stellar feedback. Similar-looking collisions can therefore produce very different amounts of new starlight. In the 20th century, Aylar and Juritam used early computer models to show just how naturally tidal gravity could create long tails and bridges. Their work helped demonstrate that many oddly shaped galaxies were not isolated curiosities, but systems caught in the middle of interactions. Later simulations by researchers, including Joshua Barnes and Lars Hernquist, followed the process in greater detail. They showed how mergers can redistribute stars, damage disks, doctored gas toward galactic centers, and ultimately produce structures very different from the galaxies that began the encounter. One of the clearest real examples is the Antennae Galaxies, a pair undergoing a major interaction. Long tidal tails stretch away from the system, while overlapping regions inside contain intense star formation, produced as large clouds of gas are disturbed and compressed. Bright clusters of young stars shine through the disturbed galaxies. A system takes its name from the enormous curved tails extending outward like antennae. Yet even such a dramatic transformation unfolds very slowly by human standards. A merger may take hundreds of millions of years, and in some cases 1 billion years or more. The galaxies approach, pass close together, distort one another, move apart, and then return under gravity. Eventually, their central regions combine and a new system begins to settle. Even after the centers merge, the aftermath is not neatly contained. Some stars are left on extremely wide orbits. Others remain in-stream. Smaller satellites may have been disrupted during the event. Tidal debris can wander through the outskirts for billions of years. The remnant, therefore, carries visible traces of its past long after the main collision becomes quiet. In the faint outer regions of large galaxies, astronomers can sometimes identify stars that once belonged to completely separate systems. Those stars are the scattered remains of galaxies that approached too closely, were pulled apart, and gradually became part of something larger. This is one of the main ways giant galaxies grow, not only by collecting fresh gas or merging with equals, but by absorbing smaller neighbors. Astronomers sometimes call this galactic cannibalism. The phrase sounds dramatic, but the process is simply a natural consequence of hierarchical formation. As small structures appear early and larger systems assemble gradually, then many dwarfs and satellites will eventually be incorporated into more massive hosts. That absorption can take billions of years. A small satellite may begin far out in the host galaxy's dark matter halo, following a wide orbit that seems almost stable. Yet as it moves through the surrounding material, the orbit slowly begins to change. The satellite's gravity disturbs nearby stars and dark matter, leaving a gravitational weight behind it. That weight pulls backward on the satellite. Through dynamical friction, orbital energy and momentum are gradually transferred into the surrounding material. The satellite's orbit shrinks, and instead of circling forever at the same distance, it spirals slowly inward. As it moves closer to the host, tidal forces become stronger, and another process begins to dominate: tidal stripping. The near side of the satellite feels a stronger pull from the host than the far side. When that difference becomes large enough, material in the satellite's outskirts is no longer securely bound and begins to peel away. Dark matter is often stripped first because its halo extends much farther than the visible stars. Gas may be removed as well. Globular clusters can be pulled away, and eventually individual stars begin escaping from the shrinking satellite. Those stars do not scatter randomly. They continue along orbits related to the path of their original galaxy, producing long, narrow stellar streams. A stream can stretch for tens of thousands of light years while wrapping around the host like a faint ribbon. The surviving core of the satellite may still sit somewhere along the stream, while stars during earlier passages trail far ahead and far behind. Over time, however, even a narrow stream begins to blur, because its stars do not all share exactly the same orbital energy. Some stars gradually move ahead, others fall behind, and the stream spreads through a process known as phase mixing. Eventually, its original shape becomes difficult to recognize, even though the stars themselves remain as part of the host galaxy's diffuse halo. The Milky Way is doing this right now. One of the clearest examples is the Sagittarius dwarf spheroidal galaxy, a small system that has been orbiting the Milky Way and repeatedly passing through regions where tidal gravity is strong enough to tear material away. Its original structure has been heavily disrupted. Stars stripped from Sagittarius form an enormous stream that wraps around our galaxy. By mapping the positions and motions of those stars, astronomers can reconstruct portions of the dwarf's orbit and learn about the Milky Way's gravitational field. In a quiet sense, the Milky Way carries fragments of former companions through its outskirts. Those fragments are not merely debris, they are records. By reading them carefully, astronomers can begin reconstructing events that happened billions of years ago. This effort is known as galactic archaeology. Instead of excavating layers of soil, researchers study stellar ages, motions, orbits, and chemical compositions. A star can preserve information about where and when it formed long after its original galaxy has disappeared. Stars born from the same broad reservoir of gas often begin with related chemical patterns. Astronomers can compare the relative abundances of elements such as iron, magnesium, calcium, and other products of stellar nucleus synthesis to search for shared origins. This approach is often called chemical tagging. If a group of stars shares both unusual elemental fingerprints and related motions, that combination can suggest that they once belonged to the same smaller galaxy or star-forming environment. The reconstruction is rarely perfect. Billions of years of mixing can blur the evidence almost beyond recognition. But chemistry provides a clue that gravity does not easily erase. Globular clusters can preserve related information as well. Globular clusters are dense, roughly spherical collections of old stars, sometimes containing hundreds of thousands of members. Some formed within the main body of a large galaxy, while others appear to have originated inside smaller galaxies that were later absorbed. When a smaller parent galaxy is destroyed, one of its globular clusters may survive as a compact trellis orbiting the new host. Its age, chemical pattern, and motion can reveal that it formed somewhere else. The same kind of accumulation occurs on far larger scales as well. At the centers of galaxy groups and clusters, giant galaxies can grow through repeated mergers with surrounding companions. Over billions of years, smaller systems lose orbital energy, spiral inward, and donate stars to the central galaxy. Yet not every stripped star ends up belonging clearly to one galaxy. Inside rich clusters, some stars are pulled so far from their original hosts that they orbit within the gravitational potential of the cluster itself. Their combined glow is known as intracluster light, a very faint illumination spread through the spaces between galaxies. These wandering stars are another archive of past interactions. The outskirts of galaxies and clusters are filled with such records: streams, shells, diffuse halos, scattered globular clusters, and barely visible structures containing fragments of systems destroyed long ago. Detecting these features is difficult because their surface brightness can be extremely low. Future surveys are designed to search the faint outskirts in greater detail and uncover the delicate signatures that ordinary images often miss. The European Space Agency's Euclid mission, along with other deep imaging surveys, is helping astronomers study low-surface brightness structures around galaxies and compare those features with modern formation models. The deeper we look, the less isolated any large galaxy seems. A smooth halo can hide the remains of many smaller systems. A faint stream may be the stretched skeleton of a dwarf galaxy. A globular cluster may have crossed into galactic space inside another galaxy before becoming part of the host we see today. Large galaxies are built partly from this accumulation of forgotten structures. Yet while some of the clearest evidence lies far out in their halos, another powerful part of galactic evolution takes place in the opposite direction at the very center, where most large galaxies contain a supermassive black hole. Compared with the galaxy around it, the black hole occupies an almost unimaginably small region. But when gas begins falling toward it, the energy released can affect material across distances enormously larger than the black hole itself. A quiet center can suddenly become one of the galaxy's strongest engines of change. Supermassive black holes range from millions to billions of times the mass of the Sun. They are found in spirals, ellipticals, and many systems between those categories, suggesting that the growth of large galaxies and the growth of their central black holes are connected in some deep way. Yet the black hole itself remains tiny compared with the host. Even a supermassive black hole's event horizon can be comparable in scale to a planetary system, while the galaxy around it may span tens or hundreds of thousands of light years. It does not directly control the orbit of every star. Far from the center, the combined gravity of stars, gas, dark matter, and the rest of the galaxy dominates. A black hole's direct gravitational influence is strongest only within the inner region. So how can something so compact influence a whole galaxy? The answer is not simply the black hole's gravity. The key is the enormous amount of energy released by matter before it crosses the event horizon. Gas falling toward a supermassive black hole usually carries angular momentum, so it begins orbiting and can form a flattened accretion disk. As material gradually works its way inward, turbulence, friction-like processes, and magnetic effects convert gravitational energy into heat. The gas can become extraordinarily hot. Before disappearing past the event horizon, it may radiate tremendous energy as visible light, ultraviolet radiation, X-rays, and other wavelengths. The black hole itself stays dark. The brilliant display comes from matter still outside it. When the central region becomes powerful enough, astronomers call it an active galactic nucleus, or AGN. Some active nuclei can outshine all the stars in their host galaxies combined, even though the luminous region occupies only a tiny fraction of the galaxy's size. Active nuclei may also dock to high-speed winds. In some systems, magnetic fields launch narrow relativistic jets of particles traveling close to the speed of light. These jets can extend thousands, and sometimes millions, of light-years beyond the host galaxy. Among the most luminous active galactic nuclei are quasars. They were much more common in the younger universe, when galaxies generally contained more coal, gas, and interactions were more frequent, giving central black holes many opportunities to feed rapidly. Under the right conditions, enormous quantities of material reached the inner regions of young galaxies and powered quasars bright enough to be seen across billions of light-years. But moving gas from the outer galaxy all the way toward the black hole is not a simple journey. Gas in a disk carries angular momentum, so something must disturb its orbit. Major mergers can drive some material inward. Minor encounters can do the same on a smaller scale. A galactic bar can exert gravitational torques that gradually rearrange gas orbits. Internal disk instabilities, turbulence, collisions between gas clouds, and smaller-scale gravitational processes can carry the journey farther. Different galaxies therefore feed their central black holes through different combinations of mechanisms rather than through one universal pathway. Once a black hole becomes active, the energy released can begin changing the host galaxy. This is known as AGN feedback. One form occurs during highly luminous phases, when intense radiation and fast winds interact strongly with surrounding gas. Radiation can heat gas, while winds can drive some material outward. If enough cold gas is disrupted or expelled, future star formation may decline. Another form of feedback is mechanical, often associated with radio-emitting jets from the central black hole. These jets can punch into the hot gas surrounding a massive galaxy or cluster, inflating enormous cavities and injecting energy into the halo. That added energy can keep the gas hot, making it harder for the material to cool and sink inward. If hot halo gas cannot cool efficiently, it cannot easily replenish the galaxy's reservoir of cold star-forming material. In this way, a black hole affects regions vastly larger than its event horizon without directly pulling on every star in the system. It changes the behavior of gas. Radiation heats it, winds move it, jets stir it, outflows remove it, and by slowing the cooling of the halo, black hole activity can gradually reduce the supply required for continued star formation. This kind of feedback has become an important ingredient in modern galaxy simulations. Without some way to regulate cooling and star formation, models often produce massive galaxies that create too many stars and remain active for too long compared with what astronomers actually observe. Modeling the process is difficult because the scales are so different. Important physics near a supermassive black hole can occur across less than a light year, while the galaxy spans tens of thousands of light years and its dark matter halo extends far beyond that. A simulation must somehow connect events in a tiny central region with consequences throughout an events and throughout an enormous halo. Many details remain uncertain, yet observations reveal intriguing relationships between supermassive black holes and the galaxies that contain them. One of the best known is the relation between black hole mass and the velocity dispersion of stars in a galaxy's bulge. Galaxies with larger bulges and faster random stellar motions tend, on average, to host more massive central black holes. The correlation suggests slint growth, but the direction of cause is still debated. Perhaps black hole feedback influences the bulge. Perhaps the same gas supply and merger history help build both. Most likely, several processes are woven together. At the center of the Milky Way lies Sagittarius A, a supermassive black hole with a mass of about 4 million suns. Today it is comparatively quiet because only modest amounts of matter are falling toward it. It is nothing like the brilliant quasars seen in the distant universe. Yet the Milky Way's center may have been more energetic in the past. Vast structures known as the Fermi bubbles extend far above and below the galactic plane and may preserve evidence of ancient activity, although their exact origin is still being studied. A galaxy that seems calm today may therefore have experienced a much more active central phase before. A supermassive black hole can remain nearly dormant for long periods, then awaken when new gas reaches it and briefly alter the fate of surrounding material. That leads us back to one of the deepest questions in a galaxy's life. A galaxy can spend billions of years gathering gas and creating new generations of stars. Yet many large galaxies eventually become quiet. Their young blue stars disappear and their cold gas reservoirs decline. Star formation slows until only a faint trickle remains. A galaxy is still there. Its old stars still shine, but its era of prolific stellar birth is largely over. What causes the transition from a creative, active system to a quiet one? When astronomers call a galaxy dead, passive, or quenched, they are not saying that every star has gone dull. Existing stars can survive for billions of years, evolving into red giants, white dwarfs, neutron stars, and black holes according to their masses. What has changed is the birth rate of new stars. A sustained and significant decline in star formation is called quenching. To keep forming stars, a galaxy needs cold, dense molecular gas. Anything that removes the gas or stops it from reaching the right conditions can reduce stellar birth. The gas may be consumed, heated, dispersed, swept away, or stabilized against collapse. One visible consequence is a change in color. Actively star-forming galaxies contain many hot, massive, short-lived stars that shine strongly in blue and ultraviolet light. Passive galaxies contain far fewer of these young stars. Their light is dominated by older, cooler populations, making them appear redder overall. This broad difference produces a useful pattern when astronomers compare galaxy color with stellar mass and star formation activity. Many active systems occupy a region known as the blue cloud, while passive galaxies gather along the red sequence. Between them lies the green valley, where galaxies often show intermediate colors and reduced star formation. The green valley is therefore a useful place to search for systems that may be moving from active to quiet. But color alone can be misleading. Dust can absorb blue and ultraviolet light, making a vigorously star-forming galaxy look much redder than it truly is. Astronomers therefore combine color with spectra, infrared emission, gas measurements, and other indicators of recent stellar birth. Only then can they distinguish a truly passive galaxy from one whose star formation is merely hidden behind us. One simple route to quenching is gas exhaustion. Every generation of stars consumes some of the cold molecular gas in the galaxy. If that reservoir is not replenished quickly enough, the available fuel slowly declines and star formation becomes increasingly difficult to sustain. A related process is called starvation or strangulation. The galaxy may still contain cold gas in its disk, but the larger external supply feeding it from the halo or cosmic web is reduced. It begins living only on what it already has. For a while, stars continue to form. Gradually, the remaining gas is consumed, heated or expelled, and the star formation rate drops. In other galaxies, the halo itself becomes part of the problem. This is sometimes called halo quenching. Inside a sufficiently massive dark matter halo, infalling gas can be heated to very high temperatures. Rather than flowing inward while cool, it forms an extended hot atmosphere. If that gas cannot radiate energy efficiently, it can remain suspended far from the disk. A galaxy may therefore be surrounded by enormous amounts of matter while still lacking the cold, dense gas needed for new stars. Feedback can strengthen this effect. Massive stars and supernova inject energy into gas, and in smaller galaxies may even drive some of it away. In massive galaxies, activity around the central supermassive black hole may become especially important. Radiation, winds, and jets from an active nucleus can heat the halo, disturb the gas, or keep it from cooling efficiently. A black hole does not need to empty an entire galaxy in one spectacular event. It may be enough to repeatedly make the fuel supply harder to maintain, so that over time the rate of star formation falls farther and farther. There is an even subtler possibility. A galaxy can keep gas and still fail to form stars efficiently. This idea is known as morphological quenching. Research by Marie Martig and collaborators explored how a galaxy's internal structure can change the stability of its gas. If a galaxy develops a massive central bulge, the gravitational environment of the disk changes. Gas may remain present, but the disk can become more resistant to the instabilities that normally compress material into dense star-forming clouds. In other words, a galaxy can possess fuel without being able to use it efficiently. The gas must not only exist, it must be cold enough, dense enough, and arranged so that gravity can overcome pressure, turbulence, magnetic fields, and large-scale orbital stability. This helps explain why there is no single universal cause of quenching. A dwarf may lose gas through stellar feedback. A massive galaxy may be unable to cool its hot atmosphere. Another may be affected by black hole activity or by the stabilizing influence of its structure. Some galaxies simply consume their gas faster than it can be replaced. Others experience several of these effects together. Galactic death, then, is less like one fatal event and more like many possible routes toward the same quiet result. Some systems appear to stop forming stars unusually quickly. These are often called post-starburst galaxies. Their spectra show evidence that a large population of stars formed relatively recently, yet current star formation has already fallen dramatically. They occupy an especially revealing transitional state. A strong burst of star formation has ended, but the stellar population has not yet aged enough to resemble a fully passive galaxy. For a short time, we can catch the system between two very different phases. Post-starburst galaxies may therefore offer clues about rapid quenching through mergers, gas depletion, or energetic feedback. Even then, however, a quiet galaxy is not necessarily quiet forever. Fresh gas can arrive later. A merger may deliver new material. Gas in the halo may eventually cool. An interaction can compress gas that had previously remained stable. Under the right conditions, star formation can begin again, a process sometimes described as rejuvenation. So the life of a galaxy does not always follow one irreversible path from blue to red, active to passive. Some fade slowly, some shut down rapidly, some remain quiet for long intervals, and some begin forming stars again. Location introduces another powerful influence on that journey. A galaxy drifting through a quiet part of space experiences one kind of evolution. A galaxy falling into a crowded group or massive cluster experiences another. There, the environment itself can strip gas, heat material, disturb orbits, and reshape the galaxy from the outside. Galaxies do not live in isolation. Some spend most of their lives in relatively calm surroundings, while others become members of groups and clusters where neighboring galaxies and shared gas can influence almost every part of their long-term development. A galaxy group is a collection of galaxies bound within a larger shared gravitational structure. Our local group is one example. It contains the Milky Way, Andromeda, the Triangulum Galaxy, and dozens of smaller systems, with the Milky Way and Andromeda among its dominant members. Galaxy clusters are larger still. A rich cluster may contain hundreds or thousands of galaxies moving inside an enormous common dark matter halo, and the space between those galaxies is not empty. Much of it is filled with extremely hot, extremely thin gas. This intracluster medium can reach temperatures of tens of millions of degrees and emit strongly in X-rays. Although the gas is far thinner than any atmosphere on Earth, a galaxy moving rapidly through it can still experience a persistent pressure against its own interstellar material. One of the most important effects is ram pressure stripping, described in classic work by James Gunn and J. Richard Galt. As a galaxy moves through the hot intracluster medium, the surrounding gas can push against gas inside the galaxy and gradually remove it. A loose analogy is the pressure felt by an object moving through air, although cluster gas is vastly more diffuse. A galaxy can travel through it at hundreds, or even more than 1,000 kilometers per second. And over time the continuous pressure can matter greatly. Stars are mostly unaffected because they are compact and interact primarily through gravity. Gas is far easier to move. If ram pressure becomes strong enough, cold interstellar gas can be swept out of the disk, removing the raw material from which future stars would otherwise form. Some of the most striking examples are jellyfish galaxies. They trail long streams of stripped gas behind them as they move through a cluster. The tails can extend tens of thousands of light years beyond the main stellar body. Dense pockets inside those tails can sometimes continue forming stars even after the gas has left the disk. For a while, the galaxy can appear to be shedding pieces of itself into the surrounding cluster. But gas removal is only one environmental influence. Gravity becomes complicated in a crowded cluster as well. A galaxy feels the pull of the cluster as a whole, and if that gravitational field changes significantly across the width of the galaxy, tidal forces can remove loosely bound stars, gas, and dark matter from its outskirts. Close passages with neighboring galaxies add further disturbances. Many encounters in clusters are too fast for immediate mergers, so a smaller galaxy may experience repeated high-speed flybys over billions of years. The accumulated effect is known as galaxy harassment. Each individual encounter may be modest, but repeated gravitational nudges can gradually change stellar orbits, thicken a disk, distort its shape, and strip material from the outer regions. A delicate spiral can become noticeably more disturbed after enough encounters. Another quieter mechanism is environmental strangulation. Before entering a group or cluster, a galaxy may carry an extended reservoir of halo gas capable of cooling and replenishing the disk. In a denser environment, that outer supply can be stripped or prevented from remaining bound. The cold gas already inside the disk may survive for a while, so star formation continues. But the replacement supply has been cut off. Gradually, the galaxy consumes what remains and becomes quieter. This transformation can even begin before the galaxy reaches the main cluster. Clusters grow by absorbing smaller galaxy groups. A galaxy inside one of those groups may already have experienced interactions, gas loss, or reduced star formation before the entire group falls into the cluster. Astronomers call this preprocessing. So when a transformed galaxy is finally observed inside a cluster, not every part of its history necessarily happened there. Some changes may belong to an earlier environment, and cluster conditions do not always suppress star formation immediately. Sometimes external pressure compresses a galaxy's own gas. Gravitational encounters can disturb clouds and increase their density. Under the right conditions, the first response may be a temporary increase in star formation, rather than an immediate decline. The outcome depends on the galaxy's mass, its gas supply, its path and speed through the cluster, and how strongly feedback responds afterward. A short burst of star formation may therefore come before the longer process of gas loss and quenching. Over long periods, environmental effects help explain a broad observational pattern. Dense cluster cores contain a higher fraction of elliptical and lenticular galaxies, while actively star-forming spirals are more common in less crowded regions and toward cluster outskirts. Environment is not the only cause, but it clearly matters. Gas can be removed, disks can be heated, small galaxies can be repeatedly disturbed, mergers can alter structure, and fresh material can be cut off. A galaxy's appearance records not only what happened inside it, but where it has spent its life. This brings the story naturally back toward home. The Milky Way looks like one coherent barred spiral today, but its stars preserve traces of ancient mergers, absorbed companions, and structures that existed before the present disk took shape. By combining stellar motions with chemical signatures, astronomers can begin reconstructing how our own galaxy was assembled. The Milky Way is not a pristine object with one simple origin. It is a layered history written in stars. More than 13 billion years of growth lie behind the galaxy around us. Gas has arrived from the cosmic web. Generations of stars have formed, aged, and died. The disk has been disturbed and rebuilt, while smaller galaxies have approached and gradually been absorbed. Internal structures such as the central bar have also developed and changed. The Milky Way is therefore not one ancient object that appeared early and remained nearly untouched. It is an accumulation of many overlapping histories. Its present structure reflects that complexity. Most familiar stars, including the Sun, belong to the galactic disk. Within it lies a relatively thin component containing much of the cold gas dust and ongoing star formation. The Sun sits in this disk roughly 26,000 light-years from the galactic center. Surrounding the thin disk is a thicker stellar component whose stars extend farther above and below the plane, tend to be older, and generally follow less orderly orbits. Near the center lies a dense bulge crossed by the Milky Way's elongated stellar ball. Far beyond the bright disk stretches a much fainter stellar halo containing ancient stars, globular clusters, and streams left behind by disrupted satellites. A much larger gaseous halo surrounds the galaxy as well, containing hot and cooler material that can circulate between the Milky Way and intergalactic space. Beyond all of this lies the still more extended dark matter halo. That dark halo contains most of the galaxy's mass and reaches far beyond the visible stars. Within this large gravitational structure orbit many satellite galaxies, some substantial and others containing remarkably few stars. Each component preserves a different piece of the past. Ancient stars in the halo and central regions formed before the modern thin disk settled into its current form. Their chemistry records the composition of the gas from which they were born. Their motions can also reveal whether they formed inside the early Milky Way or arrived later as part of another galaxy. This is where galactic archaeology becomes especially powerful, and one of its most important tools has been the European Space Agency's Gaia mission. Gaia measured the positions and motions of enormous numbers of stars with extraordinary precision. It tracked proper motion across the sky, improved stellar distance estimates, and provided radial velocity info for many stars moving toward or away from us. Combined, those measurements allow astronomers to reconstruct stellar motion through three-dimensional space. The Milky Way becomes something like an archaeological site that is still moving, with stars scattered across the sky today yet sharing related orbital histories. When related motions are combined with similar chemical patterns, ancient merger debris can emerge from the background. One of the most striking examples is known as Gaia's sausage in Celeste, a large population of stars thought to be debris from a substantial galaxy absorbed by the early Milky Way. The unusual word sausage refers to the elongated pattern made when the velocities of these stars are plotted in a particular way. Their orbits are strongly radial, carrying many of them deep toward the inner galaxy and then far back into the halo. And Celeste became another name associated with the same broad ancient merger. Researchers including Amina Helmi and collaborators helped identify coherent stellar motions and chemical evidence linked to this large accreted population. A progenitor galaxy appears to have been substantial, though still much smaller than the Milky Way is today. Its merger occurred when our galaxy was still developing and contributed many stars to the halo, while likely influencing the structure of the early disk as well. But Gaia's sausage in Celeste is only one chapter. Astronomers have identified many other streams, clumps, globular cluster associations, and possible merger remnants. Some are confidently linked to known satellites, others remain uncertain or debated. Ancient debris becomes increasingly difficult to recognize as billions of years pass. Stars once packed inside one galaxy can spread across enormous volumes of the halo, and the signatures of different merger events can overlap. Internal processes in the Milky Way can sometimes produce patterns resembling accreted debris as well. The record is therefore less like a perfectly preserved diary and more like a manuscript revised many times, with older sentences still visible beneath newer ones. A thick disk provides another example of that complexity. It contains older stars extending farther above and below the galactic plane. Ancient mergers may have heated an earlier disk, increasing the vertical motions of its stars. But merger heating is probably only part of the story. Some thick disk stars may have formed naturally in a younger Milky Way when the gas-rich disk itself was thicker and more turbulent. Radial migration may also have rearranged stellar populations over time, and the process of destruction has not ended. The Sagittarius dwarf spheroidal galaxy is being torn apart by the Milky Way today. Repeated passages through our galaxy's gravitational field have stripped enormous numbers of stars from it. Those stars form the Sagittarius stream wrapping around the Milky Way. The interaction may also have disturbed our disk, helping create ripples and waves that remain detectable in stellar motions. Another important companion is the Large Magellanic Cloud. For many years it was treated as a relatively modest satellite, but modern measurements suggest that it may be considerably more massive than once thought. It may also have entered the Milky Way's immediate neighborhood relatively recently in cosmic terms. Because the Large Magellanic Cloud is so massive, it does not simply orbit an unmoving Milky Way. Its gravity pulls back on our galaxy, influences estimates of the Milky Way's motion, disturbs the dark matter halo, and affects the trajectories of other satellites. So even now the Milky Way remains unfinished. Cold gas forms stars in the disk. Supernova throw material into the halo. Some gas later returns. A central bar rearranges stellar and gaseous orbits, while satellites continue interacting with the disk and halo. Fresh material is still being added and all merger debris is still mixing into the galaxy. What looks stable on a human lifetime is, on longer scales, a structure in continuous motion. And across about 2.5 million light-years of space lies another giant spiral, Andromeda. Andromeda is the other dominant large galaxy in the local group. For many years, the future of the Milky Way and Andromeda was described almost as an inevitability. They were approaching, gravity would pull them together, and eventually the two spirals would merge. But predicting the future of such a complicated system requires more than knowing that two large galaxies are moving closer. Their sideways motions matter. Their total masses matter. A Large Magellanic Cloud matters, and the Triangulum Galaxy can matter as well. Once those uncertainties are included, what once sounded settled becomes a more interesting question. Are the Milky Way and Andromeda truly destined to collide, or is a close passage without a merger still possible? Andromeda is the nearest large spiral galaxy to us, roughly 2.5 million light-years away. Under dark skies it can be seen with the unaided eye as a faint hazy patch, the combined light of hundreds of billions of stars. Measurements along our line of sight show that Andromeda is approaching the Milky Way. For many years that fact supported a familiar prediction. In roughly 4 to 5 billion years, the two giant spirals would meet. The usual picture had them passing through one another, becoming gravitationally entangled, making several close approaches, and finally settling into one larger remnant. The scenario became so familiar that it was often repeated almost as certainty. But knowing that an object is approaching is not the same as knowing exactly where it will be billions of years from now. A critical uncertainty is sideways or tangential motion across the sky. Imagine a distant object moving toward you. If its path is almost perfectly direct, it may eventually reach your position. But if it carries enough sideways velocity, it can pass to one side. Galaxies follow the same principle, only on a far larger scale. Andromeda's motion toward us is relatively easy to measure because it changes the wavelength of its light through the Doppler effect. Its sideways movement is much harder because, at a distance of millions of light-years, Even a substantial transverse speed appears incredibly small. Yet that tiny motion can make an enormous difference over several billion years. If Andromeda's trajectory is sufficiently direct, a close encounter and merger become likely. If its tangential motion is larger, the galaxies may pass at a greater distance. And because gravity continually alters both trajectories, even a near miss could lead to complicated future orbits rather than a simple flyby. Astronomers have therefore worked for years to improve the measurements, especially using precise observations from the Hubble Space Telescope. Hubble observations have been especially important for estimating Andromeda's tiny motion across the sky, while Gaia has refined our knowledge of stellar motions throughout the local group. But even perfect measurements of the two largest galaxies would not make the future simple. The Milky Way and Andromeda do not float alone in otherwise empty space. They belong to the local group. Triangulum is another substantial member, and the Large Magellanic Cloud, though smaller than the Milky Way, is massive enough to alter calculations of our galaxy's motion. Every major body pulls gravitationally on the others. Change the estimated mass of the Large Magellanic Cloud and the Milky Way's trajectory shifts slightly. Change Triangulum's orbit and Andromeda's future can shift as well. The masses and shapes of the dark matter halos matter too. Small uncertainties in position, velocity, and mass today can grow into very different outcomes when projected across billions of years. A local group's future is therefore a many-body gravitational problem rather than a simple-to-galaxy collision. Recent modeling has made this especially clear. Instead of calculating one idealized future, researchers have explored many possible local group histories consistent with current measurements, allowing uncertainties in masses, positions, and motions to propagate forward through time. The result is much less deterministic than the older popular picture. In some sets of modern simulations, the Milky Way and Andromeda merge. In others, they experience a close passage without merging within the next 10 billion years. This does not make the earlier predictions foolish. They reflected the best data and assumptions available at the time. What changed was the precision of the measurements, the number of bodies included, and the willingness to treat uncertainty as part of the answer rather than something to hide. A future merger remains entirely possible. So does a near miss. Better measurements of Andromeda, the Magellanic Clouds, Triangulum, and the surrounding dark matter halos may shift the probabilities again. The destination of the local group is still being refined. There is something fitting about that uncertainty. Even a prediction involving the future transformation of our entire galaxy becomes more nuanced as the measurements improve. But if the Milky Way and Andromeda do meet closely, the event would reshape both systems on an enormous scale. Their dark matter halos would begin interacting long before the bright stellar disks overlapped. Tidal forces would distort the disks, stretch spiral arms, and pull stars and gas outward into long tails and bridges between the galaxies. The disks could warp dramatically. During a close passage, stars from the Milky Way and Andromeda would occupy overlapping regions of space. Yet direct collisions between individual stars would still be extraordinarily rare because the distances between stars are so large. The solar system would therefore be very unlikely to experience another star striking it directly. Its orbit within the galaxy, however, could change substantially as the combined gravitational field rearranged billions of stellar trajectories. The Sun could be moved farther from the center of the eventual remnant, while other stars might be thrown onto wide halo orbits or even become unbound. Gas would have a more turbulent experience because interstellar clouds can collide, shock, and compress. Gravitational torques could drive some gas inward, and compressed regions might briefly form stars more rapidly. But by then both galaxies will be billions of years older, so the amount of cold gas still available would strongly determine how dramatic any future starburst could become. After repeated passages, dynamical friction could gradually remove orbital energy from the two galactic cores. The familiar spiral patterns might disappear, and stars from both galaxies would become mixed into a single, much larger gravitational system. depending on the remaining gas and details of the encounter. The remnant might eventually resemble a large elliptical or another smoother system rather than to recognizable spirals. And near the center, a second, slower merger would still be waiting. The Milky Way's central black hole has a mass of roughly 4 million suns, while Andromeda hosts a substantially more massive one. The black holes would not collide the moment the stellar disks first overlap. At first, each would remain embedded in its own galactic core. Only after the cores themselves came together would dynamical processes begin drawing the two black holes into a tighter common orbit. Eventually they could form a gravitationally bound binary, circling one another inside the center of the merged galaxy. Interactions with stars and gas could continue shrinking that orbit. If the black holes ultimately merged, the final stage would release an enormous burst of gravitational waves, long after the first visible encounter between the two galaxies. The informal name Milkomeda is sometimes used for an imagined Milky Way Andromeda remnant. But it is only a nickname, not an official astronomical designation, and with the future encounter itself uncertain, it should not be mistaken for the guaranteed name of a guaranteed galaxy. Its story begins with the faintest irregularities in the early universe. Tiny differences in density gave gravity slightly different amounts of matter to work with. The denser places pulled a little harder, gathered more material, and slowly amplified their original advantage. From those nearly invisible beginnings grew the filaments, sheets, clusters, and voids of the cosmic web. Dark matter played a central role, gathering into halos long before mature galaxies existed and creating gravitational basins into which ordinary matter could fall. Hydrogen and helium collected inside those halos. Some gas was heated by shocks, some radiated energy and cooled. In the densest regions, gravity continued compressing matter until the first stars finally appeared and the dark universe began to shine. Those first stars immediately changed their surroundings. Their radiation heated and ionized gas. Their winds moved material outward. Their deaths returned matter to space, and nuclear reactions inside them began enriching the universe with elements that had barely existed before. Carbon, oxygen, silicon, iron, and many other elements accumulated across successive stellar generations. The chemistry of galaxies slowly became richer, and with that enrichment came new ways for gas to cool and new ingredients from which later planetary systems could eventually be assembled. Dust grains formed. Molecular clouds became more complex. The atoms needed for rocky planets were created, dispersed, and recycled long before Earth existed. A history of galaxies, therefore, became connected to the later possibility of planets, oceans, chemistry, and life. Meanwhile, fresh gas continued arriving from the cosmic web. Because that material carried angular momentum, much of it did not fall straight into the center. As it cooled and exchanged angular momentum, it settled into rotating disks inside much larger dark matter halos. Early disks were often thick, turbulent, and irregular, disturbed by incoming gas, internal instabilities, and frequent interactions. Over time, some became the broad rotating systems we recognize as spiral galaxies, although their graceful appearance never meant that they had stopped changing. Spiral-ons are dynamic patterns. Stars and gas move through them. Some arms behave like regions of enhanced density, while others may form and dissolve through temporary gravitational instabilities. Nearby companions can also pull on a disk and strengthen its spiral pattern. Bars can arise inside disks and redistribute angular momentum. They can guide gas inward and reshape central regions. Bulges may grow through mergers, rapid early formation, or slower internal evolution. No single route creates every galaxy we see. Lenticular galaxies occupy part of the space between familiar spirals and ellipticals, retaining a disk and central bulge while showing little obvious spiral structure and relatively little active star formation. Ellipticals preserve yet another kind of history. As stars move through a wider range of orbits rather than remaining concentrated in one thin rotating plane. Some ellipticals were shaped by major mergers. Others grew through many smaller mergers, and giant central ellipticals can continue expanding through gas-poor encounters that mainly had existing stars. Galaxies' appearance therefore records both internal dynamics and external experience. The systems that look almost identical today may have reached that appearance by entirely different paths: quiet growth, repeated encounters, or the blending of several once independent galaxies. Dwarf galaxies make the hierarchical nature of this history especially clear. They may be small, but they are fundamental building blocks. Some remain independent, some orbit larger hosts, and countless earlier dwarfs were probably torn apart while massive galaxies assemble. That process continues today. Minor mergers add stars, gas, and dark matter. Major mergers can reorder entire galactic structures. Tidal forces draw out streams and tails, while dynamical friction slowly brings satellites inward. Tidal stripping removes dark matter first from extended halos, then gas, clusters, and stars. Over time, a once independent satellite can dissolve into the larger host, leaving only a faint trail through the stellar halo. Those streams can wrap around a galaxy for billions of years before phase mixing disperses them. Even when the original satellite has disappeared completely, its stars can remain as an archaeological record of something that no longer exists as a separate object. Much of the visible universe has been assembled from vanished pieces. At the centers of most large galaxies, supermassive black holes add another influence. Their direct gravity dominates only the central region, but matter falling toward them can release enormous amounts of energy. An accretion disk can radiate intensely before gas crosses the event horizon. Radiation heat surrounding material winds Dr. gas outward, and relativistic jets can reach far beyond the visible galaxy. Through these channels, a tiny central region can affect the future supply of star-forming gas. AGN feedback can determine whether gas cools, stays hot, escapes, or remains available to form new stars. Eventually, many galaxies become quiet. But galactic death is not disappearance. The stars remain, orbit, age, and slowly evolve. What declines is the production of new stars. Cold molecular gas may be consumed faster than it is replenished. Fresh gas from the cosmic web may be cut off, or a massive halo may keep incoming material too hot to cool efficiently. Stellar feedback can disperse or remove gas. A central black hole can keep halo gas hot. A massive bulge can even stabilize a disk against gravitational collapse. Several different mechanisms may lead to the same outward appearance of a quiet, red galaxy. Groups and clusters add more possibilities. Ram pressure can strip gas, repeated encounters can heat and distort disks, tidal forces can remove material, and environmental strangulation can separate a galaxy from the extended reservoir that once replenished its cold gas. Even here, the word death must be used softly. Quenching is not always permanent. A merger can deliver fresh gas. Halo material can cool later. An encounter can compress gas that had remained stable, and star formation may briefly return. Galactic evolution rarely respects neat beginnings and endings. The Milky Way is a familiar example. It looks like one barred spiral today, yet within it are the remains of galaxies that once had independent histories of their own. Streams in the stellar halo trace disrupted satellites. Ancient stars preserve chemical fingerprints of different origins. Gaia Sausage and Celeste records a major accretion event from the distant past, while the Sagittarius dwarf is still being pulled apart today. A large Magellanic Cloud continues tugging on the Milky Way. Gas still circulates between disk and halo. Stars are still being born. The central bar is still rearranging orbits. Our galaxy is not a finished object, and beyond it Andromeda is changing too. For years, a Milky Way Andromeda merger in roughly 4 to 5 billion years was presented as one of astronomy's familiar future certainties. A modern picture is less definite because the result depends on details that are extraordinarily difficult to measure precisely. Andromeda's sideways motion matters. So do the masses of the galaxies, the Large Magellanic Cloud, Triangulum, and the wider gravitational structure of the local group. A merger remains possible, and so does a close passage that does not end in immediate union. That uncertainty feels appropriate. Galaxies have never been objects with simple, fixed destinies. They are evolving arrangements of moving matter. They grow through accretion, change through star formation, reorganize internally, collide and absorb smaller systems. They lose gas, enter quiet phases, and sometimes become active again. Even a galaxy with almost no new stars is still orbiting, interacting, shedding material, responding to gravity, and changing within an expanding universe. What appears permanent across a human lifetime is only a temporary fall on cosmic scales. Spiral arms shift, stellar streams disperse, clusters evolve. Even the Milky Way is only one present chapter in a history that began long before the sun and will continue long after the solar system is transformed. So a galaxy is not a motionless island hanging forever in the dark. It is an immense gravitational pattern made from stars, dust, dark matter, black holes, and the remains of earlier structures, a pattern that survives not by staying the same, but by continuously becoming something new.